Okay, and our third and last speaker in this session on new water sources is Dr. Menachem Elimelech from Yale University, where he's he's got a long name here. The Roberto C. Gozzieta Professor of Chemical and Environmental Engineering, yes. And he was the founding director of the Environmental Engineering program at Yale. He also is a Clark Prize laureate from 2005 and also a member of the National Academy of Engineering. He's one of the world-renowned experts in membrane processes, including something I find really fascinating, and I think he's going to tell us about it today, and this is forward osmosis. Yes?
I think.
Good, please.
Thank you, Bruce. Few things for Shivaji. I was not planning to grade you, but you did very well. And I think in my classes at UCLA, you did even better. So I will not tell the grades here. Anyway, I think we heard enough about wastewater. And now let's talk about something that is cleaner and more exciting, seawater, and more specifically, seawater desalination. So let's see. Okay. So I will start with a slide that's showing the 10 global challenges for the new millennium. And the timing, I think, is quite appropriate because it's a list put together by Richard Smalley. And Pedro, the recipient of this year Clark Prize, worked with Richard Smalley, and indeed his talk will be also on nanotechnology. So it's not surprising when you look at this list that we see energy and water at the top of the list. And indeed, what I'm going to show you in this talk, that energy and water are interrelated. By the way, if you look at the other challenges there in the list, many of them are either directly or indirectly related to water and or energy. So we all know that there is a global water scarcity, and those of you who are here in Southern California and Arizona, we know that there is also regional water scarcity. We hear about it in popular magazines like National Geographic, books, and even some coined the term that water is the next oil. So as the title of this session, I mean, we need some new water sources, and when you think about how to increase the available water supply, there are many ways to do it, but the only way to increase it beyond what you can get from the hydrological cycle is to turn to engineering by either desalinating seawater and brackish water, and my talk will focus on desalination of seawater, or reuse of wastewater that we heard a lot in, including this session. And the challenge here, as always, is to develop a sustainable and energy efficient technology. So this will be the focus of my talk. I mean, sustainability and energy efficient desalination. So desalination got a lot of coverage, and you, again, in Science magazine in 2006, desalination was highlighted as one of the ways to fight global water shortages. The same thing in Nature in 2008, and even there was a NRC, National Academy's report on desalination that was also published in 2008. So when you talk about seawater desalination, there are several technologies, but the leading technology of any new desalination plant that will build nowadays is reverse osmosis technology. You can see some other technologies in the Gulf country, like thermal desalination, that are not energy efficient, and I will not discuss them. And indeed, as I indicated, many of the new plants, like the one in Israel, in Singapore, they're using a reverse osmosis technology. And this technology involves, again, intake, pre-treatment, which in principle is similar to the way we treat water for drinking water supply. And then reverse osmosis. This is the stage that removes the salt from the seawater to get fresh water. And also you go through some post-treatment that has some important role, especially when you use water for agriculture, like the case in Israel and in Spain. Now, we will relate to this later, the energy, but if you look at the thickness of these lines, it's just proportional to the energy that each of these processes consume, and not surprising that the RO desalination stage consume the most energy. So a few things about seawater desalination. In principle, it offers unlimited and steady supplies of high-quality water. Again, the ocean is vast, and again, there is no way you can deplete the ocean. It's plenty of water. It also produces fresh water without impairing the natural ecosystem. If you use a lot of groundwater, rivers or lakes, you can deplete the water, and water is very, very important for a healthy ecosystem. So here we do not have this problem. However, there are some limitations. The energy consumption by desalination is quite intensive. It's about 3 to 4 times more than what you will do when you treat just surface water, for example. And also there are some concern about some potential environmental impacts for desalination, which I will also discuss briefly in this talk. So in last year I've invited to write a review article in Science that talk about, again, the title was The Future of Seawater Desalination. We address several aspects in this article, and here I will highlight some of them, and specifically I will try to answer these 4 questions. Again, the talk will be general. I will not get to very details about, experiment in our lab and so on, just the big picture, and hopefully at the end of this talk, I'll provide you answers to these 4 major questions. First, we ask what is the energy efficiency of current desalination technologies and how much we can improve them. Secondly, again, we hear a lot about materials, and we pose a question, can novel materials reduce the energy consumption of desalination? Because we're reading a lot about such papers that claim that they can reduce the energy of desalination by some novel materials. Third question is, are there any innovative systems that can further reduce the energy of desalination beyond what we have now for reverse osmosis, which will be the gold standard for me for comparison? And lastly, here I will just touch upon it. It's a very big question, but general question, is seawater desalination a sustainable technological solution to global water shortages? So let's start to go through each of these questions, and I will focus mostly on the first 2 and the last 2 with some details. So the first question is, what's the current energy efficiency of desalination and how much we can reduce the energy? And I will start with a chart here that shows the power consumption in the desalination, and this is just by the reverse osmosis stage, without pretreatment and post-treatment. Since the 1970s, again, the first desalination plant by reverse osmosis was built in 1970. And as you see, there was a dramatic decrease in the energy of desalination. We started at very, very high values of 15 watt per cubic meter or per ton of water. And we dropped now, if you look at this region, although I don't have any data beyond, this is for the time that we, again, wrote the article roughly, it didn't change much. Now, we can zoom on this part here, and you see that the energy leveled roughly at about 2 kilowatt hour per cubic meter just for the RO stage. And this is the best available data, mostly from published literature or some people who claim that they can achieve it in some plants. But mostly we refer to the refereed journal articles or some respectable report to get this data. Now here you see a dashed line, and I would like to elaborate on this dashed line. This is the minimum theoretical energy for desalination based on thermodynamics. You can do some calculation assuming a reversible thermodynamic process, again, and calculate what's the energy to separate salt from water. I'm emphasizing it's independent of the mechanism or technology. You cannot come up and say, I have a different process and I can do it better. This is independent of the process. And when you do these calculations, assuming a reversible thermodynamic process, which means it will be practically infinite in size and not practical, but this is the lowest you can ever get. And if you take seawater with 35,000 ppm, and for 0% recovery, just taking 1 drop of the ocean, it's 0.76 kilowatt hour per cubic meter. And if you go to 50% recovery, the typical recoveries of a seawater desalination plant, it's about 1.1 kilowatt hour per cubic meter. So there is no way in the world that you can do it better by any process that you will ever imagine. So just remember this value. Now, if you think about this minimum energy of desalination, when you think about reverse osmosis plant, the way we operate it now, we have a pressure vessel with about 6 modules. You can think about it that the water enters at the beginning of the vessel, and as the water permeates, the salinity of the brine increases. So suppose you start with the osmotic pressure of the seawater, and as you move along the module, the osmotic pressure increases until you reach the end of the module, and this is the brine. So the minimum energy of desalination based on a reversible thermodynamic process is just following this line. If you were able to follow this line and just apply just little more pressure than the osmotic pressure, you'll have some water going through. And if you follow this one, this is practically the minimum theoretical energy based on reversible thermodynamics. Anything above it, these are the irreversible energy losses that you have. Now remember this part, the way we operate reverse osmosis, we must apply a pressure at least equal to the osmotic pressure of the brine, because if you will not do it, the water will not permeate from the modules that are here. So you need to have at least this osmotic pressure, and this will be very important when I talk about the minimum energy or the practical minimum energy for actual planes. Now, in reality, you need to apply slightly more pressure because we have this phenomenon of concentration polarization. You get slightly elevated concentration on the membrane surface, and as the water flow in the pressure vessels, you have some pressure drop. And roughly, we operate at about 10 to 20% more just to compensate for this pressure drop. So the actual pressure that operates should be at least this value. You cannot operate less than it because water will not permeate through the last modules that you have here. So just summarize these values of the energy. The theoretical minimum energy, again, for 50% recovery, the theoretical minimum energy based on reversible thermodynamics is 1.016. We can define another minimum energy, and this is not based on thermodynamics. We call it the practical minimum energy. This is just because the way we operate desalination plant, as I showed you here, we must operate at least at a pressure that equal to the osmotic pressure of the brine. If you start with 35,000 ppm seawater, the brine will be 70,000 ppm, and the osmotic pressure roughly about 54 bar. So if you assume that there is no pressure drop and the pumps are ideal, the pressure recovery devices recover all the energy that you have in the brine, then this energy should be 1.56 kilowatt hour per cubic meter. Now, as I indicated, based on report, and some reports are from the Affordable Desalination Coalition in California, they claim that some plants approach about, or some RO stages approach 2 kilowatt hour per cubic meter. And this is when you have very clean seawater without fouling and so on. Just remember this value. This is the practical minimum, about 1.6. This is the current one. So you see that there is not much room for improvement here. Now, however, when you look at some recently constructed desalination plant and the energy that they claim that they use, surprisingly, they claim anything between 3 to 4 kilowatt hour per cubic meter. For example, one of the desalination plant that was built in Israel, in Ashkelon, they claim it's about 4 kilowatt hour per cubic meter. And I will talk about it later. It's mostly through some other stages that you need there beside the RO stage that consume the energy. So again, just to summarize this part, again, the RO stage consume 2 kilowatt hour per cubic meter. The plant, at least based on what they reported, 3 to 4 kilowatt hour. So where is the rest is being expended? We will have some that go through pre-treatment, but again, pre-treatment is like a typical water treatment plant. We know roughly it can be 0.3, 0.4 kilowatt hour per cubic meter. You can also, another phenomenon, you need to increase the pressure to compensate for fouling. The way you operate the reverse osmosis at a constant water flux. So as desalination progresses and you get fouling, you need to increase the pressure to maintain the flux, and this is another component. And another very important one, and this is why the values in Israel are quite high, is the post-treatment. In Israel, they use a lot of the water for irrigation, and many crops are very sensitive to boron and also to chloride. Indeed, they want to reduce the chloride to a low level because eventually all the wastewater in Israel are being reused. And if you start with water you drink with high chloride, also the wastewater will have very high chloride. And since these wastewaters are used for irrigation, in the desalination plant, they want to reduce the chloride and the boron levels. So they go through 1 or 2 additional reverse osmosis stages that consume more energy. So, and of course, there are some other things that you have here, like intake and discharge. So here I showed you is roughly the values of the energy, what thermodynamics dictate, what's the practical minimum energy, and what's the current energy. And now let's see how we can improve, or if we can improve and reduce the energy of desalination. So let's start with the question, can novel materials reduce the energy consumption? Because we've seen many papers and people promise that they have this magic membrane that will really reduce the energy, and you will do it almost with no energy. So And here I'm focusing only on the RO stage, how we can reduce the energy in the reverse osmosis stage. And one hot area was this high permeability membrane. Indeed, when you read some of these articles or reports, they promise quantum leap in desalination, something that will be almost with no energy. And the rationale for these studies was, if this membrane has such high permeability, I will need very, very little pressure to let water go through, and then I will not use a lot of energy. But unfortunately, this is not the case, as you're going to see very soon. I will just highlight some of these studies that talk about this high permeability membrane, namely the aligned carbon nanotube membranes and the aquaporin membranes. So the aligned carbon nanotube, they found theoretically and experimentally, if you let water go through carbon nanotubes, which are some, again, nanomaterials, the water that flows through the tube will be flowing 10,000 times faster than what you calculate based on the Hagen-Poiseuille equation, just based hydrodynamics. And they were able to prove it experimentally also. They were not able to show a high salt rejection by these carbon nanotubes, but again, they are progressing toward this. So this is one thing that you can get high water permeability. And similarly, if you take aquaporin, these are the water channels that we have in any cell. And again, water through these aquaporin flows very, very fast, much faster than what you expect based on this opening of the channel. Indeed, the water flow there is roughly comparable to flow through carbon nanotubes in terms of order of magnitude. And the idea was, if you can incorporate this aquaporin into some synthetic membrane, you can get high flux membrane and reduce the energy. So I would argue that this is not the case, because the way we operate reverse osmosis, the flux in reverse osmosis is governed by the osmotic pressure of the concentrate. As I indicated, you must apply at least pressure equal to this osmotic pressure of the concentrate, which is 54 bar. And as I said, you need to apply even a little more, 10% more, because you have concentration polarization and pressure drop. And it just happened that the thin film composite polyamide membrane, that we are the gold standard for desalination, already operated at this range. Typical reverse osmosis seawater desalination plant work at this pressure, about 54 bar plus 10%, around 60 bar. So the current membranes already meet this requirement. And if you have higher permeability membrane, maybe you think you will have less membrane area. But those of you who are in this field from the practical side or the theoretical side, you know that if you put here very, very high permeability membrane, and you know that concentration polarization, if you look at the governing equation, is proportional to the exponential of the water flux over the mass transfer coefficient. If you even double the water flux more than we have now, concentration polarization will be so severe that you will not, you will immediately drop all the driving force. So in a way, this is not the way to reduce the energy of desalination. And I would argue that much more gain will be done by having fouling resistant membrane. And as I indicated, the way we operate desalination plant, once you have fouling, you need to increase the pressure to maintain the flux, and this adds more energy. Now, why it's important to have a controlled fouling in reverse osmosis membrane? Because we are stuck nowadays with this polyamide membrane. This is the best membrane that you can have for desalination. People try in the last 20 years to have some other formulation, and we are still stuck with this FT30 patent that was in the 1980s, polyamide membrane. You cannot have any other polymers for seawater desalination. You can have it maybe for brackish water. And unfortunately, this polyamide membrane has many, many properties that make it prone to fouling. The membrane is relatively hydrophobic. Polyamide is relatively hydrophobic, which is not good for organic fouling and biofouling. It has a rough surface. The way we make this membrane by interfacial polymerization, the process inherently forms a layer, active layer, which is very rough. You cannot change it. This is the way it works. And this active layer is about half micron. Again, we know that roughness can also enhance fouling. It's well known from laboratory and also from experience. It contains carboxyl group, and carboxyl group are not good, because once you have carboxyl group and you have organic matter and calcium in the water, you get some complexes and you get very severe organic fouling. Also, also one thing that I not mentioned, some of the chemistry, but it's a polyamide, and it's very, very sensitive to oxidants like chlorine. Once you have chlorine, you will degrade the membrane. You will attack the amide link, and you will degrade the membrane. So we cannot use chlorine to control biofouling. So all these properties make it very, very prone to fouling, and despite the very extensive pretreatment, we need to clean the membrane frequently, and we always need to increase the pressure to maintain the water flux through the membrane. So I would argue, and I will not show you any results, we have a lot of work in our lab to develop a fouling-resistant membrane, so I will argue that you need to have fouling-resistant reverse osmosis membrane. Also, you need to have chlorine-resistant membrane, and it's very difficult because, as I told you, the membrane company is trying for 20, 30 years to have other formulation, and unfortunately, they cannot come up with different formulation than polyamide, because you need to have this 99.9% rejection for seawater desalination by one pass, and you need to have this high water flux. So my argument, if you will develop this kind of membrane, which is not easy, especially the chlorine-resistant membrane, then you can improve the energy use of RO, and you can reduce the use of chemicals, and chemicals are used extensively for cleaning, and it's not sustainable. And also, you can reduce the pretreatment and energy cost because you can use even less strict pretreatment. So this was question number 2. I mean, if novel materials can reduce the energy consumption, and the message that I want you to take, not high flux membrane, but fouling resistance membrane. So now let's talk about, are there any innovative systems and technologies that can reduce the energy consumption? And at the onset, I will tell you, and soon you'll see that reverse osmosis technology improved dramatically, and now it's almost perfect in terms of energy consumption. You know, you have 2 kilowatt hour currently. The practical minimum is 1.6. So there are some rooms for improvement, but not significantly. But let's show you some ideas. Remember this curve. This is the minimum energy, and anything above it is the irreversible energy losses that you have. This is the extra that you get. In principle, you can have a 2-stage RO, that you get one stage that you just apply a lower pressure and filter a certain amount of water, not to get this 50% recovery part of it. And then you take the brine and go through another stage, and then you bring it to the higher pressure, and you filter another part of the water to achieve this 50% recovery. If you look at this diagram, this is roughly the energy that you will save. And you can do some calculations. And again, Professor Yoram Cohen from UCLA did these kind of calculations. And he shows, as I indicated, if one stage, the practical minimum energy was 1.56. If you have 2 stages, you drop to 1.28. Now, if you were able to ride on this curve, which is the thermodynamic minimum of energy, in principle, if you have infinite number of stages, you will approach the thermodynamic limit of desalination, the 1.06. But it will be very difficult to do it. Again, if you do some calculation, probably if you have only 4 stages, you already get very, very close. But again, I think it's well known. I mean, principally, I think the membrane companies know about it. The problem is here, you have increase in capital costs. We think, especially in academia, energy, the lower energy. But people that make this unit and sell this desalination plant think also about capital costs. So if you have 2 stages, you will have much more capital costs. And although you save a lot of energy, they think it's not appropriate. Now, again, there are here some more people who are more in the industry, and again, it's a question for them to think if it's worthwhile. But there is a way to reduce the energy of desalination of reverse osmosis to get relatively very, very close to this thermodynamic limit. Now, there is no way in the world that you can do it less than 1.1. It's just impossible. So I would like just to mention, again, Bruce indicated, I would just say a few words about some other technologies. And again, it's technology that we developed at Yale in 2004 or 5 for the osmosis. And the idea here, it's not that I'm going to show you that you can use less energy, but I'm going to show you some process or concept that you will use less electricity, because it depends what kind of energy you will get. And here, if we can find some, again, this is based on forward osmosis. Forward osmosis is, instead of using hydraulic pressure, you use osmotic pressure. So if you have the seawater here, if you put another solution on the other side of the membrane with higher osmotic pressure, water will flow here. But again, what we are doing, if we take water from the seawater and moving it to another salt, what's the big deal? The point here, if we can come up with some solution that we call it thermolytic solution, if you can find some solution that you can eventually use waste heat, that again, as Bruce indicated in his talk, otherwise this waste heat is being discarded in a power plant. If we can use it to separate this thermolytic solution so we can use it again and get the fresh water, then we can get desalination with much, much less electricity, because the electricity that you will need will be mostly just to pump the water for the cross flow across the membrane, and all the energy, which will be very substantial if you think about the energy, will come from a waste heat. So although the energy is quite large, because we know the thermal processes are not as efficient, it will be just with no cost. So there can be several solutions. One solution that we came up was the ammonia carbon dioxide, that if you dissolve ammonia and carbon dioxide in water, you can get these ammonium salts that can create very high osmotic pressure. And if you apply then waste heat at atmospheric pressure, it's 58 degrees, and it's typically heat that you cannot use to produce electricity by steam turbine or anything. So then you can decompose, again, this thermolytic salt to ammonia and CO2 and get fresh water. In the recent NAMS, North American Membrane Society meeting, Fuji Films came up with a solution that almost similar. They use CO2, but instead of ammonia, they use trimethylamine. Again, it's ammonia with 3 methyl group rather than hydrogen. And you see now that more people come up with things, but it seems that all of them roughly around CO2 and some form of ammonia. So the last question, and again, it's a loaded question, is seawater desalination a sustainable solution to global water shortages? Here I will just briefly talk about it. Again, when you look at the reverse osmosis desalination plant, these are the potential interaction with the environment. You can have an intake structure, and I think Shivaji mentioned, or some other speakers mentioned, some other way to have some intake structures that minimize impingement and entrainment of some marine organisms. You can have, again, power plant that produce the electricity. This is one of the main components. And you can also have a discharge to the ocean. It's hard to see it here, but this schematically is illustrated here. And you discharge now a brine, which is twice as much concentrated than seawater. So again, at this stage, we are not sure about the impact of this. And we highlighted a lot in this NRC report that I mentioned. I was a member of the committee of the NRC report on desalination. And there are not many, not even any field studies that really show long-term effect of a discharge of brine on the marine environment. But again, one of the recommendations is things that we need to study more. So what I would like to really talk and show you some values of what's the impact of this electricity that you use for desalination. So let's have it through some example. Again, as I indicated, one of the really major concerns for desalination is the greenhouse gases or the electricity. Of course, you will see all these environmentalists, they will, it's not that I discount them, but some of them that are not scientifically based, and they claim it will poison our ocean and all kind of things. Of course, we need to study it, but it's not the case. I think through engineering solution, we can have a proper intake structure and also proper discharge of the brine with the right diffusers and hydrodynamics and location and so on. But the part that we cannot really overcome is this electricity, because there is a limit that's set by thermodynamics for how much electricity you can use. You cannot do it lower than a certain value. And let's take an example. For some existing plant, the existing plant desalinate between 3 to 5 kilowatt hour per cubic meter. You can go to some reports and show all the existing plants, and roughly this is the range. Now, let's take some typical value. We know how many kilowatt hour we need to produce 1 cubic meter of fresh water, and we know what CO2 emission for when you make electricity to produce this kilowatt hour. So you can calculate that you will have 1.6 kilogram of CO2 per cubic meter of fresh water. Let's take example of Spain. Spain completed, and by this year they met their goal to have 1 billion cubic meter per year of desalinated water. Israel, in 1 year, they will have 500 billion of cubic meter per year. So let's take this value, 1 billion cubic meter per year. If you do the calculation based on again, you know, the kilowatt hour here that you will take an average. And if you look at this kilogram CO2 per cubic meter and do the calculation, you will emit 1.6 billion kilograms CO2 per year. So it's quite a large number. It's equivalent to several 100,000 cars more that added to the roads, and you need to consider it. And the problem here is that you cannot really reduce it much beyond. Again, with some improvement, you can bring it down, but you cannot eliminate these emissions. So I would like now to conclude so we can catch up with time. And rather than have a typical conclusion, I would like to have some recommendations that we discuss them in the Outlook, the last section of the Science Review article. So these were taken verbatim from the review article here. So let's start with the first one. So although several options currently exist to augment freshwater sources, we talked about recycling wastewater, conservation and so on. We know now that, and it's clear that these options alone will not be enough to meet the water need. We need more than this. Water conservation we need to do it, but it's not enough. This first statement that I highlighted in the beginning. Secondly, while seawater desalination must be considered after all other options have been implemented, so we recommended that you need to look at all the other options, conservation, diversion of water as long as it doesn't affect the ecosystem and so on. But in our opinion, seawater desalination should be viewed as a crucial component of the portfolio of water supply options. Again, we talk about portfolio of water supply options, and it should be one of them. You cannot just live without it. And then for water-scarce countries or regions, like, I don't know, Arizona and those places, or California, that already implement all other measures for freshwater generation, if they already try everything, and this is, for example, the case in Israel, they try everything until they decided to go to seawater desalination, then for this case, desalination may serve as the only viable means to provide a water supply. So again, this is sort of like, at least the view of myself. I wrote this article, but I think it's in line of many here in the room that the way they think. So lastly, I would like just to thank the people who did all the work and the funding agencies. Thank you very much.